Okay, let's continue with the sampling distribution related with the chi-square distribution. Actually, our main starting point will be normal again, and later slides. So sampling distribution related with chi-square distribution. Chi-square distribution is a special case of gamma distribution, which is a positive defined right-skewed distribution. So the chi-square distribution is a special case of gamma distribution. It is a right-skewed distribution with a positive range. So negative values can never be seen here. Usually measurements like waiting time in a queue, waiting time in a bus stop. So those kind of measurements, lifetime, so they follow right-skewed shape, chi-square gamma type distributions can be used here. Also, when we have a standard normal distributed random variable, square of that follows chi-square, so the range should be positive. So in real life, so you already know what is chi-square in real life, where you can see chi-square distribution, I believe, from your probability course. So, So usually appears to describe the behavior of lifetime or waiting time or time until certain event. So usually we ended up with chi-square distribution in these real life problems. So they are all measurements, behavior of lifetime, waiting time, or any type of waiting time, and time until certain event. So I don't know which gamma type you use, but in the course I will use this gamma type. When x is distributed as gamma, gamma distribution has two types, alpha and beta. Alpha parameter is related with the shape of the distribution, and beta is about the scale of the distribution. Okay. So beta parameter is about the variability, and alpha is about the shape. So we will learn these how to define the location parameters. So we have three types of parameters: location parameters, scale parameters, and shape parameters. Some distribution may have more than one shape parameters. So they have more complex behavior. So 2 or 3 different shape parameters can be defined the whole structure of a random variable. So these parameters are not related with the location for gamma distribution. So when we look at the PDF form of gamma distribution with unknown parameters alpha and beta, so we have gamma function, gamma alpha, beta to the alpha. I will use this notation, okay? And e to the minus x over beta. So x is positive and all parameters are positive. Okay, so without the range of x, it is not a probability distribution. So you have to give the mathematical form of the PDF, and also you have to give the range of a random variable where this function defined. So when x is less than infinity, less than 0, okay, so this function takes value 0. It's not defined like that, okay, so it's very important. So please write your PDFs with its range. Okay, you know gamma function actually. I believe you may know it. So it is just x to the alpha minus 1 e to the minus x dx. The range is from 0 to infinity. So this is the mathematical form of the gamma function. And if alpha is discrete, then gamma alpha function can be defined by alpha minus 1 factorial. Okay, and also one more important behavior, or we can write this also as alpha minus 1 times gamma alpha minus 1, and actually after writing this form we ended up with alpha minus 1 factorial. The one important thing that we are using is gamma 1 over 2 is the square root of pi function. Okay, what else I can tell you about gamma? Yeah, I think that's enough for now. So here I told you that the chi-square distribution is a special case of gamma distribution. So when our scale parameter beta equals to 2, that is when x distributed as gamma with alpha over alpha and 2, okay, so the shape parameter is the same but the scale parameter is 2, so this is known as chi-square distribution with 2 alpha degrees of freedom. This 2 alpha defined by the degrees of freedom. So you know the definition of degrees of freedom, I believe. Okay, and it has some characteristics like if x distributed as chi-square with new degrees of freedom, then its expectation will be the same as its degrees of freedom. Sorry, this should be x. And the variance of x will be 2 times. If you remember, for gamma distribution, the expected x is the multiplication of the parameters, and variance of x is alpha beta square. Okay, so from here we get the quantity. So when we define it like that, so in terms of gamma, what is the form? So the second parameter should always be 2, scale parameter. Then if the expectation of is new, then this should be nu over 2. Okay, so you can define your chi-square in terms of gamma like that, and then you can easily use this PDF for chi-square. You don't have to memorize a PDF separately for chi-square distribution. Just remembering the gamma and the special case form will be enough to get the PDF of chi-square distribution. Okay. So it has certain properties. So let me give them as theorems, then we can also prove them. Okay, so theorems related to chi-square distribution. So when x is gamma distributed, alpha and beta, then let's show that y equals to x over beta distributed as chi-square with 2 alpha degrees of freedom. Okay, so usually we are using these information in memory, but you can prove this. Okay, so here we are using again moment generating functions. It's very easy to use moment generating functions for such purposes, but you can use also Jacobian transformation. But I believe this is the easiest way to deal with this transformation. So you know, this is the form of the MGF or gamma distribution. So we want to find the moment generating function of y. So let's write it in terms of the definition of moment generating function. So then let's replace let's replace y by its form, which is 2x over beta. Okay, so now actually this is the moment generating function of x where t is replaced by 2t over beta. Okay, then we know the moment generating function of x. So this is then we have to replace t by 2t over beta. Okay, then 1 minus, okay, so we have beta, replace t by 2t over beta minus alpha. This beta terms goes out and we have 2t minus alpha. Okay, so now this is the beta parameter. Okay, so the same form. Okay, so we have beta, instead of beta we have 2, we have minus alpha, we have minus alpha. Only change is in beta parameter, so it has the same form. So this means that y, so let me write it this way. So this is the range of t should be t over 1 over 2 after the transformation. Okay, so the MGF of gamma with parameters alpha and 2, or same, this is same as chi-square 2 alpha. Multiplication of these two parameters will be the degrees of freedom. So y distributed as chi-square 2 alpha. We prove it. Okay, another theorem related to chi-square distribution is the sum of the chi-squares. So we have a sample of size n. Let's say they are all independent. We don't have random sample assumption here. Chi-square distributed random variables. Since they are not identical, they all have different alpha parameters. We assume it like that. Alpha and degrees of freedoms respectively. Okay, then the sum, which is y summation xi. So do you remember the distribution of that? Sum also has a chi-square distribution where the degrees of freedoms are all summed. Okay, actually this will be summation xi is a statistic. So this will be the sampling distribution of summation xi. I'm using all capital letters for random variables. Okay, so let's prove it again using the moment generating function approach. It will be very easy. You will see how easy it is. But you have to know the moment generating function form of the gamma distribution to be able to do it easily. So moment generating function of t. So if you remember the properties of moment generating function under the independence, we have the multiplication of each random variable. Okay, so you have to remember this property of moment generating function to be able to solve it easily. Without that, actually you can use the definition of moment generating function and write the moment generating function of y as e to the expectation of e to the ty, and replace y by summation xi, and then you will you will end up with the same formula. Actually, you don't have to memorize it if your memory is not good enough like mine. So 1 minus, so we have chi-square beta value 2, alpha values each alpha I. Okay, and then after multiplying this, only alpha terms are changing, so we have 1 over 2t minus summation alpha I terms, I from 1 to n. Okay, and t should be less than 1 over 2. Okay, so this is exactly the same as moment generating function of chi-square distribution, where alpha is changed as summation alpha. Okay, so the MGF of chi-square with summation alpha I degrees of freedom. Okay, so this is the proof. What else? Oh, okay, another theorem. If x is standard normal distributed, then you know that the square of that distribution of x square is distributed as chi-square with 1 degrees of freedom. Actually, here you can, if you want, you can use Jacobian method, but I also use the moment generating function form. Okay,